direction telling that you are solidifying. And if you are above Tm, the same function will essentially move in this direction, giving you melting. All the while returning the structure of the interface. Okay, this is what the picture I want to create. So now the question is, how do I do this? All right. To do this, I will essentially allude to something you already know. All of you know about this is a diffuse interface, right? Right? Diffuse interface, which I'm calling as, because this interface is not sharp, it is diffuse, right? So let's look at something which is not diffuse but related to diffusion. Okay, so I'm not calling it diffuse, but I'm alluding to the term diffusion because some of you would have heard about this equation, diffusion equation, right? So let's start there. So you like heat diffusing or species diffusion? Huh? Species diffusing or heat diffusing? Don't go to sleep. Huh? Heat diffusion, okay. You like heat diffusion? Okay. Okay. Right? Let's say this is your equation. And let's say I have one material block, let's say A at temperature T1, another material block at T2, right? If I put them in contact, how will the temperature field start to evolve? Huh? So first we need to ask which is the higher temperature. Let's say T1 greater than T2. So how will the profile change? So you'll start with a profile which is T1, right? How will this evolve with time? Is this okay? This is okay? And eventually they become the same temperature, right? Now, what do you call this structure of the interface? Slightly diffuse, right? You started from a sharp one, but as the evolution is progressing, you essentially have the temperature field diffusing with time, right? So we have partly got the problem already. We wanted to create a diffuse interface, and the structure of this equation is already giving you something which is diffuse. Except that with time, this diffuseness will make it flat. It will get infinitely diffuse. So what is the end state of this problem? A flat line somewhere between T1 and T2, right? But what do I want? I want the equilibrium. That means a steady state to exist where it is diffuse, but not infinitely diffuse. It is somewhere in between sharp and flat, right? So I have some part of this equation already there, but not entirely. because it is having a situation that it becomes infinitely diffuse. All right. So, what should I do to my problem? What are the boundaries? Well, fix the boundaries, it will still be a straight line. It's not a flat line, but it's a straight line. So what do I need to do? Well, what I need to do is not trivial too. So bear with me. I'm going to ask you that I do something and you tell me what will happen if I do that. So, let's say to this equation, right, I add a term, or subtract a term, which is, let's say, quite a complicated term. You'll see why I do it. I add this term. Okay. Now tell me what will happen to this equation. Does a steady state exist? So let's see how to think about this problem. You know what happened when this term was not there, right? When this term was not there, what happened? It wanted to become infinitely flat. Came flat, peacefully. So let's take the other possibility. We added one term. So let's shut off this equation. And your starting point is let's say a state like this, some diffuse profile, where let's say this is 1, this is 0. Okay? Tell me what, if I were to shut this equation off, as a result of adding this term, what will change? How will this equation, how will this curve transform? Huh? Oh. Certainly the chickies should be tempting. So how will the curve transform? So online fellows don't get the chickies. Just to tempt, these are the chickies. Yeah. I will guide you. I mark this value 0.5 for a reason. This is not good. I marked that 0.5 equal t equal to 0.5 for a reason. Come on. Been a long day, but okay. At t greater than 0.5 and less than 1, what is the sign of the evolution? Positive or negative? positive because 1 minus 2t is negative. So here regions will try to move up. Between 0 and 0.5, what is the sign of the evolutions? Huh? Negative. Because this is positive. So total thing is negative. So eventually what will happen to this? If I start with a diffuse profile, it will go towards this. Okay? Will any evolution happen after this? No, because everything is 0. So you start from a diffuse profile. This term wants to make it as sharp as possible. Right? What does this term want to do? As diffuse as possible. Both terms are there in the equation. What do you expect? They will compete and give you equilibrium. Okay? And this therefore gives you a structurist equation, a partial differential equation, which necessarily has a steady state. That means a situation where dt by dt equal to 0. Okay? Now, just so that we're totally convinced and not taking my word for it, just put dt by dt equal to 0 in this equation. You would get an equation of this type. So, who can integrate this? We need to know what is the solution for t of x and how does it look. Nasty looking differential equation. Yes. I'll give you a trick. And this trick we'll be using multiple times during the course. Okay? First is, because here there's no time, there's only x, I will change my derivatives to total derivatives. Okay? Right? And then I'm going to multiply something on both sides of this equation so that I can integrate. Okay? What is that something? And let's say I want to integrate from x equal to 0 to some value of x. Right? Let's say I do that. What is the integration of this? dt by dx or? dt by dx the whole square. And I'm looking for a solution which is diffuse. You all agree there's a diffuse interface, right? So at x equal to 0, which is the left side of this, I'm going to assume that dt by dx is less than 0. Okay, so I can integrate to some value of dtx, which is non-zero. On the right hand side, you have a situation that this can be directly converted from an integral of x to integral of t. Okay, so if I do that, dt, and this is, let's say, let x equal to 1, x equal to 0, you will, let's say, have 1 to some value of t. Okay? So, can anybody tell me what the integration of this is? It's a polynomial. This you can check later. It's this. Okay? To differentiate that, we use this. So essentially, you have a situation that becomes t square into 1 minus t square. All right? So let's take it a step further. There was a copper here. So dt by dx will be what? Dt by dx will be which one should I take, plus or minus? Decreasing, because our boundary condition work with somewhat like this. So we have to take negative. And then can solve for t of x. So if I want to solve for t of x, how will it be? All right. And I want to integrate from x 1 to t. Right? So who can tell me what the t of x is going to be? This is a pretty routine integration. What will it be? dt over t ln t minus ln of 1 minus 1 by t. So ln of t by 1 minus t is equal to x. Solve for t. We have some exponential function, no? Yes, what does it come? So let's do the integration. See some integration context first. Is that okay? No? Yes, no? Right? Well, it's known now. Well, let's say I mean the same thing. So you have to put an integration because okay, let's remove the limits of integration, just integrate. Just integrate it such that you get this. There's a point where I'm putting the limits of integration. Just to put the I don't know why it's not there. One minus t has a negative. Check your balance again. Okay, so this is what you will get. But now I will do something intelligent in the sense that to take care of this c, I can choose where my x is starting, right? X is just a which minus sign?
Yeah, there was initially one minus. dt by dx is equal to minus square root.
Yeah, this one.
Yeah.
Okay. Fine. So this I will choose my x. I can choose my x anywhere, depending on where my t is. I will choose x equal to 0, where my t is equal to half. Okay, I can choose wherever it is. Why? Because t, if I put half, this becomes log 1. So this becomes 1. I can put x equal to 0 there, c becomes 0. Okay, so I will put my origin at the point where t is half, such that c becomes 0. Concept of integration. All right. In which case, your here is m, but we are doing t. So t upon 1 minus c will become exponential of x root of 2w by k. Is that okay? Now, if that is so, can you give me t of x? Now this is easy because you have t of x is equal to, or rather t over 1 minus t plus is equal to exponential of minus Okay, and you have to solve for t. So you'll get exponential of okay, you'll get this. How does this function look? Remember x equal to 0 is at t equal to half. How does it look? Like this, like this, like this. We'll do a little bit of lettering, see how it looks. So this is what you're looking at, right? And this is what you're solving for. Okay. Just see what I'm trying to do. Just define this term delta is equal to root of k by 2w. So define delta is equal to root of k by 2w and check whether we're able to transform this here to here. Here just the sign will be different, that's all. Just right. The only difference is this is k by 2w. I'm just writing it as root of k by 2w. Just use this delta to transform this. Huh? Huh? Minus, don't worry about the minus. Just coming. So if it is coming, then do one more thing for me, which is add half and subtract half to the previous equation and see what you get. See whether you get this. Is it coming? it all right? So that's your tan hyperbolic. Okay, you take the half, and what is inside that bracket is a tan hyperbolic. So how does the tan hyperbolic look? How does your tan hyperbolic look? It looks precisely as you wanted it. It looks like this. Okay? Alright? This is how it will look. Any doubts? Everybody get until here? Alright? So what did we do? We added something to the diffusion equation which changes the behavior of the equation from making it fully diffuse. The additional term essentially wants to make it a little bit less diffuse, and the compromise is giving you a solution which is looking like this. Okay? And this is what you want to start with. You wanted to create a diffuse interface that is stable like this, and the next point is I want to make this clear. Okay? That's what I want to do. But I have created my first job, so I have created over here. So how do I make it move it here or there? I put a driving force to it. Okay? So let's now formally do this in the language of phase field. So how do I formally do it? I formally introduce the concept of a functional. Okay? A functional, because then I will essentially introduce machinery which will result into the modified differential equation that you just solved for. Okay? My starting point will be there, here, but I will use machinery, new machinery that will be relevant for functionals and arrive at precisely the differential equation which will give a steady state solution as this. Okay? So, I'm going to formally introduce this sort of differential equation. How many of you understand this? This operator? Everybody understands? So I don't need to be afraid of not understanding. Okay, that is a functional. Okay, I'm going to be starting here, and I'm going to be basically writing down evolution equations. By the way, this is meaning a short notation for d phi by dt. Right? I'll be writing evolution equations for d phi by dt by telling that something with respect to this functional should be maintained, or something should happen to this function. Okay? But my starting point will be this. Right? Okay. So notice I have changed from t to phi because I wanted to create a phase field. That phase field, as I said, was going to be an indicator function telling me regions of the domain where certain phases are present and certain other phases are absent. Okay. All right. So now I want to basically derive evolution equations starting from this functional, right? And let's see what recipe we can adopt for doing this. Now, I'm writing this functional in this form because of certain reasons, as you will see, but this is also referred to as the classical Ln-Kahn way of doing things, Ln-Kahn equation, or rather the functional This is just a Gensburg lambda functional, but yeah, any question will come later. This is the functional I want to start with. Okay. Now, to do something to this functional, I need to derive or define an operation on this function, which is referred to as a variational derivative. Okay. Right, variational derivative, and this variational derivative is something that I will utilize to create my differential equation. Right? Now, this variational derivative is something that operates only on functionals, and it differs from the classical partial differentiation. Right? I'm not talking about I'm not talking about this. I'm talking about a new operator which looks like this. Okay? I can't talk about this because this is not a single valued function. Okay? I mean, it's not a function, because it is a function of fields, which are functions themselves. Okay? So grad phi, for example, is a field. Phi of x is a field, right? It's a function by itself. And the integral of that is a real number. So it's a mapping between a field to a real number. Okay? So you can't think of modifying a small value of phi here and find out what this is. That doesn't make sense at all. You need what you want to do is change the function a little bit and find out the resultant change in the. Okay, that's what you want to do. In the classical partial derivative, what do you do? The given function, change the value of the function at a given point in space, and ask what is the change in the. So you change in the value of the independent variable and find out what is the change in the value of the dependent variable. That gives you partial derivative. Here, we're going to change the function itself locally and ask the question, what change does it do to the integral itself? All right? Okay. So here, let's resort to some notes to avoid these writings. Okay, so let's formally introduce this. So I have my integral, we'll call it yi for some functional, but instead of phi, I'm using y. Okay. And my integral is my functional looks like a finite integer between x1 to x2 of some integrand, which has dependency on the space, on the function itself, and on its radius. Okay, that's just like as you have over there. And now, what I want to ask is, I want to change this function by a small value. How do we change the function? At a small change function, delta y. Okay, but a localized change. What do you mean by a localized change? Let's say you have a function like this, a function, very good. But I want to change this function locally at this point. So what do? I typically do is add a delta function, which is localized to change only here by a arbitrarily small magnitude, as small as it is. Okay, that will give me a small change, localized change of the function that I want to have. So I'm going to call that delta y. All right, and the question I'm going to ask is, if I do that small change, y tilde of x, y of x plus delta y of x, which you can picturize it this way. What happens to my integral? Okay, so I can define my change in the integral precisely as this, which is my change function minus the original function. Okay, and as I said, I can choose my delta y as some arbitrary small constant multiplied by a differential function, which is localized at x. Okay, and that I can call as a direct delta function. And this can be as small as it is. So this change is as small as it is. Okay. So then it all becomes mathematical generally. You have I y of x, which is the original integral, y tilde of x, which is your modified function, giving you, which is this y of x plus epsilon phi of x. But remember, this is a differentiable function. So you have y prime of x plus epsilon phi prime of x. Okay. So if I give you this function, and I tell you that you can do a Taylor series expansion now about your original function, that was f x y of x comma y prime of x. You can certainly do that.
You can turn on that mic and turn this off. If I can define a change in value of the integral as a form of this type, which has the form small function over here like this, then the variational derivative is defined as the term that is inside the bracket, the integral. Okay, it's a definition. That means if I can write down a small change in the integral as a term which looks like this, that is a term multiplied by a small function delta y, then the variational derivative of I with respect to a small change in y is the value of the integral. Okay, this is dou x by dou y, partial derivative of the integral, original function, minus dou by dou x of dou x by dou y. All right? Is it clear until now? So we have created a new operator which can work on integrals or functionals, and it is operating like this. Okay? How to picturize this? See, if you think of a derivative, you can think of it as a slope, right? How do you picturize a variational derivative? You're doing some small change to a function. The resultant change is some change to an integral. But how do you picturize it? Visualize it?
Like a moving map.
No.
Perimeter of the curved surface. Sort of like a small hump on the function does.
See, I want to think about it as a classical derivative. In a classical derivative, I do small change in the function, a small change in the dependent variable. How much does my function change? This is what I think visually, right? That's my derivative. How will I think about a variation? It's called a derivative. Called a variational derivative on top of that. How do I visualize it? Area of what? Of course, the integral is area. But area of what? See, you're changing a function, right? So remember, this is essentially what you're doing with a variational derivative. You are changing a function locally, right? That function can be changed, can be as steep as small as you please. But remember, what you're also essentially trying to control is how is its behavior in the locality. Okay? It is telling that is the functional change such that you are changing derivatives, making it more smoother or more steeper near its vicinity. Okay? And as a result of that, what you are doing is trying to change the nature of the function and trying to see the effect of the integral. Okay? How many of you have made graphs using would have made smooth curves using some drawing program, right? So in your drawing program, they give you a three-point curves where you can change in the vicinity. You can put points and change the curve like this or like this, and it will change locally the variation of the function. You can think of the variational derivative in some sort controlling the shape of the function at a locality, apart from varying the value of the function. Okay, just to give a little bit more clarity, we will try to do this in a discrete sense. Okay, in a discrete sense, the discrete sense allows you to compute things by numbers. Right? So, and that we will do it after dinner. Otherwise, all of you will miss dinner. Right? So you can just online participants, we have a crunch over here that the dinner is served only until 8:15, and we have no other place to have dinner. So we will have to have dinner and then come back. So we ask